Welcome back to the deep dive. Today we're going to do something a little different. I want to start by just asking you to visualize the word summer.
Mm-hmm.
For most of us, right, especially if you grew up in a temperate climate, that word triggers a very specific set of associations.
Sure, yeah. Long days, vacation.
Exactly. Maybe it's a beach chair, a cold drink.
Yeah.
Just that general feeling of time slowing down. We sort of culturally code summer as the off-season. It's our pause button.
It's the season of leisure, and biologically, that makes a lot of sense for humans. We've mastered our environment to the point where the seasons don't really dictate our survival in the immediate term.
Right.
But the source material we're covering today argues that this whole perspective is, well, it's a complete hallucination when you apply it to the rest of the natural world.
And that source is Summer World, A Season of Bounty by Bernd Heinrich. For those who maybe haven't encountered Heinrich before, he isn't your typical academic biologist who spends his life in a sterilized lab.
Not at all. He's more of a naturalist in the 19th century tradition, right? He's out there observing from a cabin in the woods of Maine and Vermont.
He's climbing trees, getting stung by wasps, counting pollen grains on bees.
He's getting his hands dirty, and that's what makes him fantastic because he combines that old school muddy boots observation with, rigorous physiological testing.
So it's not just observation, he's running experiments.
Exactly. And his central thesis in Summer World is that for plants, insects, birds, mammals, for everyone else, summer is the exact opposite of a vacation.
It's a frantic, high-stakes, breathless race against a ticking clock.
That's it. It's a battlefield.
A battlefield. I think that's the best way to frame it. That lazy buzzing of insects we hear isn't leisure.
No, it's the sound of a desperate scramble to secure energy and reproduce before the window slams shut. The constraints are just absolute.
So in the north, the energy spigot, the sun, is only fully open for this brief period.
And if you miss your cue by a week or even just a day, your genetic line could end right there.
So our mission for this deep dive is to unpack the specific strategies that life uses to win this race.
We're going to look at how trees basically predict the future, how frogs utilize what is essentially cryogenics, and even the psychological warfare that birds use to protect their young.
What I found most compelling, and what I want to get into, is this idea of energy budgets.
Yeah.
It really changes how you look at a simple patch of woods.
It does.
It's not a landscape painting. It's more like a stock market floor where everyone is just shouting and trading energy credits.
That is a great analogy. It really is. Every single movement, every leaf that unfurls, every bird song, it's an expenditure that has to be paid for.
So let's start with the engine that drives this whole market. We need to define summer, not as like a vibe, but as a physical phenomenon. And Heinrich makes it very clear, summer is defined by light.
It's a physics equation, it really is. And it all starts with the architecture of our solar system. You have the Earth orbiting the sun, but the key variable, the thing that makes everything happen, is the tilt.
Right, the 23.5-degree tilt of the Earth's axis.
That number is everything.
Without that tilt, we wouldn't even have seasons.
We'd be stuck in a state of perpetual stagnant equinox. But because of that 23.5-degree tip, as the Earth moves in its orbit, the northern hemisphere literally tips toward the sun.
And this changes the angle of attack for the solar radiation.
Precisely. In the winter, the sun hits us at this really shallow angle, so the energy is spread thin over a huge area. It's diffuse.
But in summer, it's coming straight down. It's direct.
It hits us head on. The energy density just skyrockets.
And that energy is what fuels the entire biological engine through photosynthesis.
Yeah.
Heinrich even breaks down the etymology there.
Making from photons. It's the primary industry of life on Earth. Plants are capturing those photons and converting them into chemical bonds, into sugar. That sugar is the currency for absolutely everything else.
The herbivores eat the plants to get the sugar. The carnivores eat the herbivores.
But here's the catch in the north. That factory can only run when temperatures allow liquid water to flow. So you have this massive influx of solar capital, but a very, very short time to spend it.
Which brings us to the first major strategy in the book, pre-packaging. This one actually blew my mind because I've always just assumed that in, say, April or May, when the weather gets nice, the trees sort of wake up, sense the heat, and just start building their leaves from scratch.
That is the common assumption. It's what it looks like, right? We see this green explosion in May, and we assume the work is happening right then.
But if a tree waited until spring to start building its solar panels, it would already be too late.
Way too late. It would waste weeks of prime sunlight just constructing the tools to catch the sunlight
So they do the work beforehand.
long beforehand. Heinrich explains that the buds you see opening in the spring, the ones that become leaves and flowers,
Yeah.
they were actually formed the previous summer, usually around July.
So right now, in the dead of winter, the trees outside are already covered in next year's leaves.
Exactly. They're just folded up in these tiny, perfect suitcases. They are fully formed, microscopic, embryonic leaves and flowers, all wrapped in these protective scales, just sitting dormant.
That's a massive investment of energy, though.
Mm-hmm.
The tree is taking the surplus sugar from this summer to build the infrastructure for next summer.
It is. It's a huge gamble.
But it feels like a really risky stock option. If you build your buds in July, they have to survive the autumn, the freezing winter, all the ice storms. What keeps them from opening too early?
That's the critical question.
Like if we get a warm week in January, which seems to happen more often now, why don't the trees just pop open?
Because if they did, the next frost would kill those tender new leaves, and the tree has lost its entire energy investment for the year. It's a catastrophic failure.
So they need a clock that's more reliable than just the temperature.
Temperature is volatile. It fluctuates wildly. They need a signal that is astronomically precise.
The photoperiod.
The length of the day. Or actually, to be more precise, the length of the night.
Heinrich brings up a classic experiment that really illustrates this mechanism. It involves cabbage butterfly caterpillars.
Right, the work by Erwin Bunning, it's brilliant. He was trying to figure out how a tiny caterpillar knows whether to keep eating and turn into a butterfly now.
Or to just shut down.
Or to shut down and go into what's called diapause, which is like insect hibernation for the winter. Because if it metamorphoses in October, it freezes and dies. It has to know the time of year.
And Bunning found it wasn't measuring the sunlight directly.
No. The caterpillar has a circadian rhythm, an internal 24-hour cycle, just like we do. And Bunning proposed that there is a specific photosensitive phase in this cycle.
A window.
A window, yeah. Let's say it's about 14 to 15 hours after dawn. You can imagine a little gate inside the caterpillar's brain that just swings open for a short window of time.
So the gate opens. If it's summer, the days are long, so there's still light when that gate opens.
Correct. If light hits that open gate, it triggers a hormonal cascade that basically says, it's summer, keep growing, full speed ahead.
But then as you get into autumn, the days get shorter.
The sun sets before that 14-hour mark. So when the gate opens, it sees darkness. And that darkness triggers a completely different hormonal pathway that says, winter is coming, shut down, spin a cocoon, and wait.
It's a binary switch that's tied to the Earth's orbit. It's so elegant.
And it's hardwired. This is why you can't fool nature easily. Heinrich talks about the groundhog or, ground squirrels and the folklore of Punxsutawney Phil.
Saturday, yeah.
People think the animal is looking at the weather. It's not. You can put a ground squirrel in a windowless room with constant temperature and constant light.
And it still knows.
It will still try to hibernate when it's autumn outside. It has an endogenous circannual rhythm. A calendar is built right into its genetics. It
just knows when the year is turned.
It does.
So the clock ticks over, the days lengthen, the light hits that photosensitive gate, and boom, we get the awakening. This is the start of the race.
And in the north, the starting gun is the thaw. It's a literal melting of the barriers.
Heinrich describes this sequence so beautifully. The skunks waking up, the chipmunks surfacing. But the most dramatic first movers are often the amphibians.
Oh, absolutely. Specifically the wood frog.
This is a creature that just completely defies what we think is biologically possible for a complex animal. We're not talking about hibernation where they, slow their heart rate down.
No, this is freezing solid.
It creates a kind of cognitive dissonance when you see it. A wood frog in February is, for all clinical purposes, a rock. It sits under the leaf litter on the forest floor.
And if you picked it up and dropped it, it would actually clink. There's no heartbeat. No breathing, no brain activity. Its blood is literally ice.
How does the cell structure even survive that? Usually when water freezes, it expands and forms these sharp crystals.
Right. It should shred the cells.
Yeah, if that happens inside a cell, it should just burst like a frozen soda can.
That is the danger. But the wood frog has evolved this incredible natural antifreeze mechanism. The second ice crystals begin to form on its skin, its liver dumps massive amounts of glucose sugar into its bloodstream.
So it floods its own system with sugar.
A huge amount. And this glucose gets packed into the cells. It acts as a cryoprotectant.
So it lowers the freezing point of the fluid inside the cell.
Exactly. And it forces the ice to form outside the cell in the extracellular spaces. So the frog turns into a block of ice, but the delicate machinery inside the cells stays liquid and intact, just very, very syrupy.
Okay, so it's a frozen, sugary rock, and then the spring rain hits.
The first warm rain of April, usually when the air hits about 40 degrees Fahrenheit, they thaw out from the inside out, the heart kickstarts, and we still don't fully understand the electrical trigger for that reboot.
Wow.
And they immediately start moving, and they all have one destination in mind.
The ephemeral pools. These temporary puddles in the woods that fill up with snowmelt, but then they dry out by summer.
Which seems like a terrible place to raise your kids, right? A nursery that's going to disappear.
It sounds like a huge risk. Why not a permanent pond?
It's a calculated risk. A permanent pond is stable, sure, but it's also filled with predators. Fish, newts, diving beetles. It's a slaughterhouse for a soft, defenseless tadpole.
Ah, so the ephemeral pool is a fish-free zone.
It's a safe haven from predators, but it comes with a strict time limit.
So they have to race against evaporation. And Heinrich describes their arrival at these pools as a scramble competition. He says it's not a courtship, it's a riot.
It is absolute chaos. Thousands of frogs can arrive on a single night. The males vastly outnumber the females, and the drive to reproduce is so high that they lose all discrimination.
What do you mean?
Heinrich describes males grabbing anything that moves, other males, floating sticks, salamanders, his own boots, anything.
And when they do find a female,
They have these nuptial pads on their thumbs, and they use them to lock their arms around her chest in a grip called amplexus. And it is unbreakable. You could physically separate the frog's legs from its body before you could break that grip.
that is intense. But I guess it makes sense given the stakes. If he lets go, 10 other males are waiting to take his place.
And you often see these mating balls, a rolling sphere of 10 or 12 males all wrestling for access to a single female at the center.
Wow. And I read that sometimes the female can actually drown in the process.
Sadly, yes. But again, from a biological perspective, the genetic drive just overrides individual survival.
So once the eggs are laid, Heinrich notices another fascinating behavior, this one involving thermodynamics. They don't just lay their eggs anywhere.
No, they laid them in a massive communal heap, almost always in the sunniest part of the pool.
A single spot.
Right. And this is a brilliant example of collective engineering. Heinrich, in classic field biology style, wades in with his thermometer to measure the temperature.
Of course he does.
And the surrounding water might be 40 degrees Fahrenheit. But inside that gelatinous mass of thousands of eggs, the temperature can be 13, 14, 15 degrees higher.
So the mass itself is trapping heat.
The dark embryos absorb the solar radiation, and the jelly insulates it. By clumping together, they create a kind of thermal reactor.
And what's the benefit of that?
Speed. Heinrich calculated that for every 3-degree increase in temperature, development speeds up significantly. They might hatch days, or even a week, earlier than a solitary egg mass would.
And in a pool that is shrinking an inch every day, a week is the difference between life and death.
It's everything, but even with that head start, not everyone makes it. And this leads to one of the darker strategies that Heinrich documents.
Cannibalism.
Yeah, it's grim, but you have to look at it through the lens of energy efficiency. The pool is running out of food, it's running out of water.
And you have a population of thousands of tadpoles all competing for both.
Right. So Heinrich observed that wood frog tadpoles are generally vegetarian. They scrape algae off of leaves. But under stress, when the pool gets crowded and shallow, some of them switch strategies.
They become carnivores.
They become what are called phenotypic carnivores. Their bodies actually change. They develop larger jaws, a different gut, and they start eating their siblings.
Specifically the ones that are already dead or dying.
Yes. It's basically recycling the energy of the failed siblings to ensure that at least some frogs from that genetic pool make it out.
It's a kind of trophic polymorphism, right? The protein boost from eating meat allows the cannibal tadpoles to metamorphose faster.
It's a ruthless equation. It's, if I eat you, I get the energy to grow legs and walk away before the water vanishes. If I don't, we both dry out and die. From an evolutionary standpoint, the cannibalism saves the genetic line.
That's the race happening in the water. Now let's look up. At the air race, the birds are returning, and they are bringing their own set of desperate strategies. Heinrich spends a lot of time on the American woodcock.
The timberdoodle. It's such a bizarre-looking bird. It's got this chunky body, basically no neck, and a beak that just looks way too long for its face.
But Heinrich explains that the beak is a very specialized tool for summer survival. The tip is flexible and sensitive.
Right, so it can probe deep into the mud for earthworms that it can't even see, but it's their display flight that really fit their theme of high stakes.
The sky dance.
This is how the male proves he is worthy of passing on his genes. At dusk, he just explodes from the ground and flies upward in a wide spiral. He goes up hundreds of feet until he's just a tiny speck. And as he flies, you hear this trilling, whistling sound.
But he's not singing, it's not vocal.
No, it's entirely mechanical. The woodcock has 3 specialized primary feathers on the outer edge of its wing. They are very narrow and stiff.
So the air rushing through them makes the sound.
Exactly. When the air rushes through them during this high-powered flight, they vibrate like the reed of a clarinet. He's literally playing his wings as an instrument.
And then comes the finale.
The free fall. He folds his wings and just plummets towards the earth like a stone, zigzagging, chirping the whole way down, and then pulls up just inches above the ground to land on his specific display spot.
Why go to such extremes? This must burn a colossal amount of calories.
It is an honest signal of fitness. That's the key. He is broadcasting to the females, look at the excess energy I have. Look at my agility. If I can afford to waste this much energy on a dance, imagine how good my genes must be.
It's a biological flex.
It's the ultimate biological flex.
So while the woodcock is flexing, other birds are engaging in subterfuge. We have to talk about the phoebe and its nemesis, the brown-headed cowbird. This is a drama that happens on millions of American porches every single summer.
The eastern phoebe, yeah. That's that friendly, tail-wagging flycatcher that just loves to build nests on human structures, under eaves, on light fixtures.
But a cowbird is a brood parasite.
Which means they completely outsource parenthood. The female cowbird just watches the phoebe build a nest. When the phoebe lays her eggs, the cowbird sneaks in.
And lays one of her own.
She often removes one of the phoebe's eggs first, then drops in her own, and then she's gone. She never sees her offspring again.
And the phoebe raises it. This is the part that just frustrates human observers so much. You see this tiny parent bird stuffing food into the mouth of a chick that is literally twice its size.
Oh, it's huge.
And the cowbird chick looks nothing like a phoebe. Why doesn't the parent bird realize what's happening?
It's a hijacking of the feeding instinct. Birds are hardwired to respond to a very specific stimulus. A gaping red mouth begging for food. The cowbird chick has evolved to have a louder beg and a wider, redder mouth. It presents what biologists call a supernormal stimulus.
It's tricking the parent's brain by basically shouting louder than the real kids.
Exactly. The phoebe's brain just says that mouth is the most hungry, it needs the food. Heinrich shares this really heartbreaking observation where a male phoebe was frantically feeding a massive cowbird chick while the female had already given up and started building a new nest nearby to try again.
Wow. He's just caught in a behavioral loop he couldn't break.
He couldn't break it.
Speaking of nests and deception, there is a fascinating mystery Heinrich uncovers with the red-eyed vireo. A small songbird, but its nest construction includes a very, very strange material.
Yeah, he noticed that vireo nests are almost always decorated with these strips of gray paper. But not just any paper, it's specifically the paper from the nests of the bald-faced hornet.
Now, getting paper from a live hornet nest is not like picking up a twig. That is a dangerous procurement.
You are risking a fatal stinging. So the question is, why do it? Is it for insulation? Is it for camouflage? Heinrich develops what he calls the scarecrow hypothesis.
Which puts us inside the mind of the predator.
Exactly. Who eats bird eggs? Squirrels, blue jays, chipmunks? What are all of those predators terrified of?
Hornets.
Hornets. A bald-faced hornet colony is a lethal threat to a squirrel. They know that gray paper pattern means stay away.
So the vireo rips off strips of this danger sign and just plasters it all over its own nest.
It's a form of Batesian mimicry, but applied to architecture. It's like saying, I am a tasty bird nest, but I am dressed up as a stinging fortress.
Does Heinrich test this theory?
He does, using his ravens. Heinrich lived with a group of ravens for years, and he took an active, live hornet nest, which is a terrifying thing to transport, by the way.
Put it in his car.
He plugged the hole with toilet paper, cut the branch, put it in a bucket, and drove it home with the hornets buzzing inside like dried peas hitting the side of the bucket.
That's dedication.
It is. He presented this live nest to the ravens, and the ravens, who are incredibly smart, they wouldn't touch it. They respected the threat.
But once the hornets were gone...
Once he presented them with an empty nest, they tore it to shreds to eat the larvae inside. which suggests that the visual signal of the paper is a powerful deterrent, but only because predators have learned to associate it with pain. The Vireo is leveraging that learned fear.
This transitions us perfectly to the architects themselves, the insects. The wasps and hornets are the ultimate summer racers because they start from almost nothing every single year.
The life cycle of the bald-faced hornet is just a masterclass in exponential growth. In the winter, the entire colony dies off, except for the newly mated queens.
They hibernate.
Right. And in the spring, a single queen wakes up completely alone.
This is the part I didn't appreciate. She is a single mother who has to build the initial house, hunt all the food, lay the eggs, and defend the fortress all by herself.
It's an incredibly vulnerable bottleneck in their life cycle, and she has to keep the brood warm. We tend to think of insects as cold-blooded, right? They just match the air temperature.
But she can't wait for a warm day. She needs her babies to grow now.
So she turns herself into a furnace.
Oh.
She uses her flight muscles. Muscles generate heat as a byproduct of movement. The queen will decouple her wings from the muscles and then vibrate them, rapidly shivering, essentially.
She shivers to generate heat.
Yes, and Heinrich measured the temperature inside that little paper envelope she builds. Even on a cool morning, she can crank the nursery temperature up to 80 or 90 degrees Fahrenheit.
That is an immense calorie burn for a single insect.
It is. She is burning through all her fat reserves to create this tropical microclimate in the Maine woods. And it's all to speed up the enzymatic reactions in the larvae. Warmer larvae grow faster.
And faster growth means the first batch of workers hatches sooner.
And once that first generation of workers hatches, the queen can retire from hunting and defense.
She becomes an egg-laying machine.
Exclusively. And the workers take over the expansion. The colony turns into a fortress factory. But that initial phase, the solitary struggle of the queen, is the linchpin of the whole operation.
Now, not all wasps are social like that. Heinrich contrasts the hornet with the mud dauber. This is a solitary wasp.
Right, the one that builds those organ pipe tubes you see on the sides of barns and houses.
With the mud dauber, there's no queen-worker relationship.
No, every female is an independent contractor. She builds a mud tube, and then she has to fill it with food for her offspring.
But she doesn't feed them daily like a bird does. She pre-stocks the pantry.
And the food of choice is spiders. But here's the problem. If she just kills the spider, it will rot before the egg hatches and the larva can eat.
And if she leaves it alive and uninjured, it will crawl away or maybe even eat the egg.
So she performs neurosurgery.
She stings it.
She stings the spider in a very precise nerve cluster. It causes permanent paralysis. The spider becomes a zombie.
Yeah.
It's alive. Its metabolism is tinking over, so the meat stays fresh, but it cannot move.
And she just stuffs the tube full of these living spiders, lays a single egg, and seals it up.
It's macabre, but incredibly efficient. When the larva hatches, it finds itself in a dark room with a pile of fresh, living meat.
But what Heinrich really highlights here is the genetic programming. This wasp has never seen a nest built. It's never met its mother.
Yeah.
It certainly hasn't been taught spider anatomy in a textbook.
It's born with the manual. Heinrich calls it an encyclopedia of instructions. The complex behavior collecting mud, shaping the tube, hunting a specific kind of spider, stinging it in a specific spot, it's all written in the DNA.
But sometimes that programming hits a glitch when it encounters the modern human world. Heinrich tells a really funny story about his heating system breaking down.
The furnace bug. His furnace stopped working, and he traced the problem to a water gauge, a clear glass tube. It was completely clogged, so he took it apart and found it was packed solid with these little green leafy circles.
It was a leafcutter bee.
A relative of the solitary wasps. Its genetic program says, find a narrow cylinder, cut circular pieces of leaves, line the cylinder, lay an egg.
And the glass tube of the water gauge was a perfect cylinder.
It was a perfect fit. The bee didn't know it was part of a furnace. It was just following the algorithm.
It just shows the incredible power, but also the blindness of instinct. It works 99.9% of the time in nature, but give it a glass tube and it can cause a mechanical failure.
Exactly.
Okay, so we're going to close our deep dive with a look at evolution in action. We've talked a lot about competition, but we also need to talk about cooperation and how cooperation can sometimes turn into exploitation. Heinrich brings us to the blue butterflies.
The lichenids. The spring azure is the one you'll see most often in the north. It's a tiny, delicate blue butterfly. But its caterpillar has a secret weapon,
A special gland.
a specialized gland on its back, a dorsal nectary organ.
It's basically a soda fountain.
It is, essentially. It secretes a sugary, amino acid-rich nectar. And ants love sugar. So instead of eating the caterpillar, the ants come and drink the nectar.
And in exchange for the sugar, they stand guard.
They act as bodyguards. If a parasitic wasp or a spider comes near the caterpillar, the ants attack it furiously.
It's a protection racket. I pay you in sugar, you keep me safe.
It's a classic case of mutualism. Both sides benefit. But then Heinrich takes us to the tropics to show what happens when this relationship is pushed to the extreme over millions of years.
Because in the tropics, the summer race never ends.
So the evolutionary arms race just escalates and escalates.
He describes the moth butterfly, Lephirapsolis. And this story, it feels like a heist movie.
It really does. This caterpillar doesn't just hire ants as bodyguards. It invades their home. It lives inside the nest of the weaver ant.
Now, weaver ants are incredibly aggressive. They have powerful jaws. They spray formic acid. Nothing is supposed to survive inside their nest.
Right. So how does a soft, juicy caterpillar survive in the lion's den?
It builds a tank.
It literally builds a tank. The caterpillar has evolved this tough, leathery skin that hangs down over its legs like a skirt. The ants can't flip it over. They can't bite through the armor. It's impregnable.
And what's it doing inside the nest? Is it drinking nectar from the ants?
No. It's eating the ant babies.
Oh, wow.
It's a predator. It just plows through the nursery, devouring the ant larvae, completely protected by its tank suit.
But here's the trap, right? Eventually, that caterpillar has to turn into a butterfly. A butterfly is soft. It has these delicate wings. The moment it emerges from its chrysalis inside the nest, thousands of angry ants should just tear it to shreds.
This is the genius of Lephera. When the butterfly hatches, it is covered in a thick layer of loose, white, greasy scales. Imagine being covered in, like, talcum powder mixed with grease.
So the ants attack.
And their jaws just get gummed up. The scales slew off instantly. The ants can't get a grip. They're slipping and sliding and spitting out these scales. And in all the confusion, the butterfly just scuttles out of the nest, finds a branch, and expands its wings to fly away.
It's the perfect getaway car.
It's the result of relentless evolutionary pressure. The ants get more aggressive, so the caterpillar gets tougher skin. The ants get better at gripping, so the butterfly gets slipperier scales.
And Heinrich also mentions a Trojan horse strategy with another species, Aropala.
Right, this one relies on chemical mimicry. The caterpillar has evolved to smell exactly like an ant larva, so the ants find the caterpillar, maybe at the entrance of the nest.
They sniff it.
And their programming says, this is one of our babies that fell out. We should bring it back inside.
So they carry it inside the nest themselves.
They carry their own destroyer into the heart of the colony. And once inside, the caterpillar just feasts on the ant brood. It's chemical hacking.
So bringing all this back to where we started, we challenged this idea of the lazy summer. After looking at the frozen frogs, the shivering hornets, the sky-dancing birds, and these tank-driving caterpillars, I think the verdict is pretty clear.
The verdict is that bounty is hard-won. Heinrich's title, A Season of Bounty, is true. There is food, there is sun. But the competition for that bounty is incredibly fierce. Every single organism is operating on a razor-thin margin of error.
The lazy hum of the meadow is actually the roar of a million tiny engines all running at redline.
It is. It's a race to capture energy and turn it into the next generation before the cold returns. The shutters of winter are always, always waiting to slam close.
And I think the so what, for everyone listening, is really about attention. Heinrich's work is this wonderful invitation to stop seeing the outdoors as just, scenery.
It adds this whole other layer of depth. When you see a phoebe on your porch, don't just see a cute bird. Look in the nest. Is there a monster chicken there? When you see a wasp, just appreciate the ancient, sophisticated software that's running in its tiny brain.
It turns a simple walk in the park into a high-stakes drama.
It really does. You start seeing the connections, the timing, the desperation. It just makes the world feel so much more alive.
So here's my challenge to you, listening right now. Next time you are outside, or maybe even just looking at a spider in the corner of your ceiling, ask yourself, what race is this creature running? What clock is it listening to? You might find there's a whole other world operating in parallel to ours, right under your nose.
And you don't need a PhD to see it. You just need to look.
Thanks for taking the deep dive with us. We'll see you next time.